Hi, we're the Miramar College Marzio Carters. My name is Tegan.
My name is Rashad.
My name is Brittany.
And my name is Min.
This is our Mars rover prototype, the Marzio Kart. It's a wireless, gesture-controlled RC car inspired by the popular game Mario Kart and designed with a Mars mission in mind. When brainstorming ideas for this project, having seen the standard rover in motion, we wanted to make controlling the robot more intuitive. To do this, we planned to address what we saw as the design choice causing the most friction, the steering. While having all four wheels spin simultaneously granted significant horsepower, it also forced the rover to come to a complete stop in order to perform a turn. Not only does this greatly impact the ease of use, it also necessitates a longer learning period for individuals attempting to control the rover.
Our main goals for the Marzio cart were to first create controls that were simple yet efficient, something that anyone could pick up and use without a steep learning curve. Second, to incorporate a way to collect visual data remotely, which is important for navigation and exploration in an environment like Mars. And third, to make the system fully wireless, so there's no physical tether limiting range or movement. The result is a rover that can turn left and right smoothly, move forward and backward, and is controlled through a custom steering wheel that you tilt to turn, with buttons for forward and reverse. A front-mounted live streaming camera lets us see exactly what the rover sees.
The frame was created in SolidWorks and 3D printed using ABS filament. We tested it repeatedly, making redesign when needed to improve strength and fit. On top of the frame, we mounted the ESP32 microcontroller, the breadboard, and the 4AA battery pack, which powers the DC motor and the servo. We attached the ESP32 using Velcro so we can remove it easily for rewiring or reprogramming.
For acceleration, we used the two DC motors mounted at the rear of the frame. They are powered by the four 1.2-volt AA rechargeable batteries, giving a total of 4.8 volts. These motors are controlled by the TB6612 FNG motor driver, which we wired to the ESP32. The motor driver takes signals from the ESP32 and controls motor speed and direction.
For steering, we designed a custom mechanism that allowed the front wheel to pivot independently. This mechanism is powered by a single servo motor. The servo rotates a rod connected to the front wheel, turning them left or right while the rover is in motion. This setup gives a smoother, more intuitive steering in the skid steering system.
The steering wheel was modeled in OnShape and 3D printed in PLA plastic. Inside, it holds an ESP32 microcontroller, an MPU 6050 accelerometer, two push buttons, and a 9-volt battery mounted underneath the breadboard.
The accelerometer detects tilt on the y-axis, left or right, and sends that data wirelessly to the rover using the ESP-NOW communication protocol. The rover's ESP32 receives the data and adjusts the servo motor to turn the front wheels in real time. The two buttons control forward and reverse movement. One button sends a signal to the rover to move the DC motors forward, and the other reverses them. This control method was inspired by the Wii Remote. We wanted something simple and familiar to most people. We chose ESP-NOW over traditional Wi-Fi control because ESP-NOW has low latency and doesn't require a constant internet connection, which is ideal for remote environments like Mars.
Our camera is a ESP32 cam module mounted at the front of the rover. It streams live video over Wi-Fi by creating its own access point. Any Wi-Fi capable device can connect to it and view the feed. For testing, we used a laptop. When wiring the RC car, we had to be very careful with pin selection. The ESP32 cam reserves certain pins for the camera module, so we had to test different pin configurations for the motors and servo. At one point, one of the motors would spin continuously during code upload. We discovered it was connected to a pin that was default to high at startup. We fixed this by moving the motor to a different pin. Another lesson we learned was the importance of battery charge. If the AA batteries or the 9-volt battery weren't fully charged, the motors wouldn't run correctly or the camera feed would cut out. This was especially important during demonstration. We also tested the range of the ESP32 cam's live video feed. It worked well for short to moderate distance, but for future improvements, we would like to add an external antenna to improve both video quality and range.
When coding the servo for the steering mechanism, we ran into an issue. If the steering wheel was tilted too far, the servo would over-rotate and risk breaking the steering mechanism. I added a software limit in the code to restrict the servo's range of motion, protecting the hardware while keeping the steering responsive.
Here's the Mario Kart in action. As you can see, tilting the steering wheel changes the rover's direction, and the buttons handle forward and reverse. The live camera feed gives the operator a clear view of what's ahead, even if the rover is out of sight.
If we had more time, we would have added a temperature sensor to gather environmental data. On Mars, this could help in assessing terrain conditions and safety. We also would like to improve the rover's wireless range and add more robust power management so the rover can run longer on a single charge.
We'd like to thank our faculty advisor, Gina Bokikio, for mentoring us, NASA and the California Space Grant for generously funding this project, and Miramar College for providing the tools, space, and time to complete the Marzio Kart. Thank you.